Greetings, hello, hi, welcome. We are almost done. So now all our enthalpies are determined at all these states. Yes, it's the same problem, but now we're about to finish it. Look at this. We have all our enthalpies, and now we just need to find what is our mass flow rate, and then we can get our efficiency. Then we are done. So enthalpy at state 1 is found. We found that enthalpy, found that one, find that, found that. All the enthalpies are found. Now in this video, what we are going to look at is how to get the extracted fraction, how to get y, and how to get z. So in this video, we'll be looking at how to find the portion of steam extracted to the closed feed water heater and the open feed water heater, the mass fraction. Alright, so to do that, we'll start off at the closed feed water heater. We'll isolate the closed feed water heater, take it as a control volume, which it is. It allows steam to flow in and flow out. It also allows feed water to flow in and to flow out. Because it's a closed feed water heater, there is no mixing of the two mediums. Steam flows in, steam flows out. Feed water flows in, feed water flows out. So that's the control volume. So I'll go ahead and do that. I'll replicate the control volume down here, and I'll indicate this is my steam coming in, and then goes in a coil, and then it leaves. The fraction is y. Since it's not mixing, y goes in and y leaves, seeing that there is no mixing. So at state 6, y is leaving. State 9, y enters and y leaves. And at the same time as that is happening, feed water enters at state 4, and at this point it is now leaving the open feed water heater. The quantity of the feed water entering is 1, because you have y here, you have z here, and you have one minus y minus z coming in, and as a result they mix in the feed water heater back again to 1. So what we have here is 1 entering and 1 leaving at state 5. So this is closed feed water heater. So taking an energy balance across the feed water heater, it's just summing what goes in, you should be equal to what goes out. It's the same thing, similar to Kirchhoff's voltage law or Kirchhoff's current law. Current going into the node must be the same as the current leaving the node. It's the same thing here. Kirchhoff says if you have a node, current that goes into the node must be similar to current that leaves the node. So it's the same thing. This simply means I1 should be equal to I2 plus I3. It's the same principle that is applied here. Energy in must be equal to energy out. So doing that, we'll have energy in must be equal to the energy out. All right. So, yeah. Question is, what is the energy that is coming in? What we have here from state 4, we have mass flowing in and mass exiting. So at state 9, you have mass flowing in and mass exiting. Okay, so treating it as per unit mass, we can just take enthalpy. So we could say enthalpy times the fraction of mass. So in this case, we have enthalpy at state 4 multiplied by 1, and what leaves? Well, enthalpy at state 5 multiplied by 1 is leaving, and we have enthalpy at state 9 multiplied by y, because it's a fraction of the, well, that's the fraction that was extracted, and H6 multiplied by y. Alright, so let's go ahead. Energy in, what goes in? We have H9, we have H4, all of those guys are coming in, so we can say H9, let's say y times H9 plus 1 times H4, and all of this I equated to H5 will multiplied by 1 plus y multiplied by H6. Right, I can rewrite this neatly as H9 plus H4 is equals to H5 plus y H6. Collect like terms, this becomes YH9 minus YH6 is equals to H5 minus H4. There's nothing to it. And then factor out Y9 minus H6 is equals to H5 minus H4. Therefore, Y is equal to H5 minus H4 divided by H9 minus H6. So that's how we get the mass fraction. So seeing that we already found out what is H5 and what is H4 and what is H9, what is H6, we can go ahead and find this value. I know that H5 is 814.59 minus, what is H4? 707.030 divided by H9. Okay, H9 was 2992.54 minus H6, which was, okay, I had the value of 814. And this gives us 814.59 minus 707.30 divided by 2992.54 minus 814.59. That gives us 0.04926. There are no units. This is a unitless ratio because these units are the same. I mean, kilojoules per kilogram divided by kilojoules per kilogram will cancel out and leaves that value as a unitless value, just a ratio. And we can do the sum to get Z. So we do this to get Y, and you also apply an energy balance across the open feed water heater to get Z, because we know that H9 comes in, that comes in, that comes in, and that leaves. So we can do that. Open feed water heater. If we apply an energy balance across the open feed water heater, sorry about that, then we'll have the following situation. We have 10 Z coming in, and we have 2 1 minus Y minus Z coming in, and we have, and they are all coming to mix inside there. Seven, this Y, and what leaves is what's leaving here. It's leaving at state 3. State 3. So 1 leaves. They all mix, and then we have 1 leaving at state 3. So applying an energy balance would say energy in should be equals to energy out. That's all it is. In other words, energy in minus energy out should be equals to 0, or energy out minus energy in should be equals to 0. That's all it is. There's nothing special about it. So I'll go ahead and write it down as H3 times 1 should be equals to Z, which is that one, times H10 plus that one. They're all coming in. So 1 minus Y minus Z times H2 plus y times h7. Yes, you guessed it. Now we collect like terms. Okay, h3 z plus h10. We can multiply, expand the brackets here, plus h2 minus yh2 minus zh2 plus yh7. Now we can collect like terms. We could say h3 minus h2 is equal to zh10 minus zh2 plus yh7 minus yh2. Finally, we'll have h3 minus h2 is equal to zh10 minus h2 plus yh7 minus h2. Therefore, what are we looking for? Looking for z. We can then say h3 minus h2 minus yh7 minus h2. All of this is equal to h10 minus h2. And then you can divide everything by h10 minus h2. Therefore, z is equal to h3 minus h2 minus y multiplied by h7 minus h2. All of this divided by h10 minus h2. Okay. Now just substitute the values. What is h3? h3 was 697 minus h2 199.33 minus, what is y, 0.04926. What is h7? at 14.59. What is h2? 199.33. All of this divided by h10. Okay, I had h10 as 2 at 52.37 minus h2 199.33. Work this out, it comes down to 697 minus 199.33 minus 814.59 minus 199.33 divided by 285 2.37 minus 199.33, and my calculator gives me 0.71. What am I writing? 0.1762, and that is just a ratio. Okay, so that's how you get Z, the extracted fraction. That's how you get the extracted fraction across a closed feed water heater and an open feed water heater. Whenever